35. CPS Geometry. Planes in Space, Part 1. We have started the CPS geometry with the definition of the CPS points. CPS points are infinitesimal spheres, in a close packing of spheres arrangement, filling up the CPS space. Next, we have introduced the concept of the CPS lines. The CPS lines are the simplest CPS patterns, formed when connecting any two CPS points. Now, is time to move to the next critical concept of the CPS geometry, the plane, or better said the CPS plane. Arguably, the plane is the most important concept of any geometry, including the CPS geometry. To do this, we will use the Cartesian space. You might ask, why do we need the Cartesian plane and the Cartesian space to explain and understand the CPS geometry? I would like you to think about this question in these terms. Try to imagine an architect leading a team at a construction site, erecting a beautiful building. Initially, the building, with its well-defined theme, structural shapes, unique design concepts and decorative details, exists only in the mind of the architect. Once the design is done, the building team needs a large scaffolding structure to make possible the actual construction. After the construction is done, and the scaffolding structure is removed, a new and incredible piece of architecture stands up by itself, in its entire splendor, ready to be admired and explored. Using this analogy, think about the CPS geometry as being the new and beautiful building being erected, and the Cartesian coordinate system being nothing more than the scaffolding needed during construction. Let us proceed. Our purpose here is to associate a CPS plane to every CPS line emanating from a CPS point. We will do that by looking for the plane, which normal is the given CPS line. To start with, let's consider the simplest plane, already encountered in our investigation. This is the plane with an underlying square lattice. The normal to this plane is the CPS line, with the unit of measurement equal with the square root of 2. One can easily see that this plane can be considered as being generated by two identical CPS lines, with the unit of measurement equal with 1. The grid generated by all identical CPS parallel lines, which can be drawn in this plane, determines the lattice corresponding to this plane. We already stated that the stack of such planes has a periodicity equal with 2. Once again, the normal to this plane is the CPS line corresponding to square root of 2. Periodic phenomena are regularly repeating patterns. CPS lines can be imagined as periodicity in space. Then, the periodicity of planes along the CPS line corresponding to the square root of 2 is equal with square root of 2. The frequency of this periodic pattern is equal with 1 over square root of 2. Let's restate our aims here. First, we want to connect the arithmetic with geometry, or more exactly we want to connect numbers with points. Second, we want to find a unified way of characterizing every possible plane that contains a given CPS point. This plane, and every subsequent plane we will encounter, can be associated with 3 orthogonal CPS lines. The detailed discussion of this simple configuration will then be extended and applied to every possible CPS plane. Initially, for this plane, we can consider the x-axis and y-axis as being two identical and orthogonal CPS lines, with the unit of measurement equal with 1. These two CPS lines generate a grid. All the nodes of this grid are CPS points. This CPS plane is a pattern generated by our initial assumption The CPS points are distributed in space according to the close packing of spheres arrangement. By replacing the geometric point, as defined in the Euclidean geometry, with the CPS point, the infinitesimal sphere, the random, unstructured and ambiguous defined Cartesian space, becomes a space with a pre-established harmony. You might have noticed that, we are using here, an extension of the concept of pre-established harmony, introduced by Leibniz. With this, the Cartesian space has been replaced by the CPS space. A closer examination of this space reveals lines, planes, and other interesting patterns and properties waiting for us to explore and understand. For example, we have just shown some CPS nodes located on each of the two axes. Any other CPS node in the grid can be considered as being located on the CPS line, connecting the origin with the corresponding CPS node. Let's see again some CPS nodes, forming the CPS lines, corresponding to the axes. As said before, these two axes correspond to identical CPS lines. As expected, the axes are orthogonal on each other, and they both have the unit of measurement equal with 1. In the same time, each node in the grid can be associated with two numbers. These two numbers are the coordinates of the CPS point relative to the two axes. This is done in exactly the same way it was done in the Cartesian plane. Why are we doing this? Simply put, we want to find all the CPS lines, starting in the origin and connecting all the CPS nodes in the grid, in this plane. More exactly, we want to find all units of measurements, corresponding to these lines. Again, as stated in the beginning, we want to associate CPS points with numbers. In doing this, we will find a deep connection between the number theory and the CPS geometry. This will put the number theory in a total new light, by providing a very useful way to visualize abstract concepts, and by opening new methods and new planes of investigations. To help us with this investigation, we will also use another well-known concept, namely the vector. In CPS geometry, the vector is an oriented CPS line segment, starting in one CPS point, and ending in another CPS point. From this definition, one can see that the orientation of a CPS vector is always along a CPS line. The magnitude of the vector is proportional with the unit of measurement, corresponding to the CPS line. The proportionality factor is always an integer number. If the proportionality factor is equal with 1, then the corresponding vector is the smallest CPS vector that exists along that specified direction of space. For example, OA is the smallest vector along this direction. We can state this by observing that OA does not intersect any other CPS node in the grid. Using a dedicated term from the linear algebra, we will refer to this vector as OA hat. We will look now, in the most general terms, at all possible CPS lines that can exist in this plane. To do that, let us consider a generic CPS node, A. Two coordinates uniquely identify this node. In our example, these coordinates are alpha and beta. Fermat's theorem on sums of two squares proves to be very helpful here. The theorem states that an odd prime number, p, can be expressed as a sum of two squares if and only if p modulo 4 is equal with 1. The prime numbers, for which this is true, are called Pythagorean primes. All the Pythagorean primes are equal with 1, modulo 4. Fermat's theorem can be extended to include all natural numbers. An integer, greater than 1, can be written as a sum of two squares, if and only if its prime decomposition contains no prime, congruent to 3, modulo 4, raised to an odd power. We can apply these results to CPS geometry. All CPS lines, existing in this CPS plane, have units of measurements equal with the square root of a product of Pythagorean primes. For example, 2450 is equal with 2, multiply by 5 square, multiply by 7 square. 7 is congruent with 3 modulo 4. Its exponent, 2, is even. So 2450 is the sum of two squares. 2450 is equal with 7 square, plus 49 square. As shown in a previous video, it is worth reminding us that the square roots of the square free numbers form a set of incommensurable magnitudes. All the CPS lines, with a unit of measurement equal with a square root of a square free number, have units of measurements which are incommensurable with each other. The Pythagorean triplets are special cases of numbers, which are sums of two squares. In this case, the result of the sum of squares is also a square number. The CPS lines, corresponding to the odd numbers, belonging to Pythagorean triplets, have units of measurements equal with the corresponding odd number from a Pythagorean triplet. Let us look to the distribution of the CPS lines, associated with the square root of 9. There are two cases here. In the first case, number 3 can be found on the square root of one CPS line, 3 units away from the origin. In the second case, number 3 is located on the CPS line, corresponding to the square root of 9. The unit of measurement on this line is 3. The last thing I want to mention here is the Landau-Ramanujan Constant. In the number theory, this constant is defined as the limit to the ratio between a large number n and the number of numbers smaller than n, that can be written as a sum of two squares. We will continue our discussion of CPS planes in the next video.